All right, guys, we are going into section 1.2. We're going to spend our time today looking at functions, as you can see there. More specifically, right here. Decide whether a relation between two variables represents a function. So yes or no, is it a function or not? Then we're going to look at function notation to use and evaluate functions. Then we're going to spend a little bit of time looking at finding the domain of functions, and then look at some real life type problems with that. So let's move on. An introduction to functions. So says many everyday phenomena involve two quantities that are related to each other by some rule of correspondence. The mathematical term for such a rule of correspondence is a relation. Here are two examples. So basically, all that mumbo jumbo is just saying that a relation is comparison of two things here. All right, the simple interest I earned on an investment of $1,000 for 1 year is related to the annual interest rate by the formula I equals 1,000R. Two variables there, I and R, they are comparing or equaling out. So this creates a relation. The area of a circle is a relation that compares the area based on the radius of the circle. Okay. So not all relations have a simple mathematical formula. For instance, you could match up an NFL starting quarterback with number of touchdown passes. There's no real formula for that, right? Ryan Tannehill, how many touchdown passes did he throw last year? Lamar Jackson, how many touchdown passes did he throw last year? That's comparing two things, quarterbacks and touchdown passes. That's a relation. The time of day and what temperature is. That's a relation. Earlier in the day, it's usually cooler. Afternoon, it's hotter. But that is a relation, comparing two things there. In each of these cases, there is some relation that matches each item from one set with exactly one item from a different set. Such a relation is called a function. So this is what we're going to look at today, is a function. Here's the definition, and then I'll give you a little simpler explanation. A function f from a set of A to a set B is a relation that assigns to each element x in the set A exactly one element y in the set B. The set A is the domain or set of inputs of the function, and the set B contains a range or set of outputs. So that's a little bit of confusing what it's saying there, but basically what it is saying is if we go back to this quarterbacks and touchdown passes, a function is characteristic of this situation. You got Ryan Tannehill, Tom Brady, Lamar Jackson. Each one will throw a specific amount of touchdowns. Ryan Tannehill at the end of this season cannot have two different amount of touchdown passes thrown. If he throws 25, he throws 25. He doesn't throw 25 and 15 in the same year. That's what makes this a function. One quarterback has one output at the end of the year, or one amount of touchdown passes. Now, there could be 5 different quarterbacks that throw 21 touchdown passes, right? You'd have 21 touchdown passes thrown by whoever. Deshaun Watson, Russell Wilson, Tom Brady, whatever. I can't think of any off the top of my head. But they could all throw the same amount of touchdown passes. But each one of those only has one amount of touchdown passes. This is what a function is. When you're talking about mathematics, it is the x and the y. The x is the input. The y is an output. All right? For every x, there can only be one y that's associated with it. Okay? The y can repeat itself, but the x cannot. The x only has one output. Okay? That makes it a function. All right, so here is the example they're talking about, time of day. Same thing. At 1 o'clock in the afternoon, there can only be one temperature. It can't be two different temperatures in one spot at 1 o'clock in the afternoon. All right. At 2 o'clock. All right. So this is sort of a I can't even think of what it's called right now, but a mapping is what it's called, a mapping. All right. If we pretend this is the X and this is the Y, all right, 1 o'clock can only go to one temperature, or the variable X can only be attached to one Y. Now, at 3 o'clock, notice at 3 and 4 o'clock, it's 15 degrees, and this is Celsius, 15 degrees at both 3 and 4 o'clock, which is fine. All right, because each one of those has two separate times. It can have the same temperature. 3 o'clock could not be both 15 degrees and 12 degrees. So each X only can point to one Y. Okay, each X can only have one output. That is a function. All right, if we look at it in ordered pairs, the way it lines up is if you have a relation where you've listed all the ordered pairs, the X's cannot be repeated, because that means one X would be paired up with two different Y's. But Y's can, right? 15 and 15. Okay. There's some characteristics. I'm not really going to go over that. That's basically what we were just saying. Let's see if they have any graphs here. Real quick before we go on to that, the way we can tell in a graph, let's look at a couple of graphs here of things that are or are not functions. Let's look at just a line, and let's look at a circle. All right. Here, a line, this line right here is a function, because each X value, we're looking at -4 here. If I go up to -4, there is only one value associated with that X value at -4. At -1, there's only one value associated. At 1, one value. 2, 3, 4, 5. At 5, there's only one Y value associated with that. And this is what we call, you can check by what's called the vertical line test. Y'all have all heard that before. If you can draw a vertical line through the graph and slide it back and forth, back and forth, back and forth, and at no time does it touch the graph at 2 points at one time, then it is a function, right? If this line touched the graph at more than 2 points, that means this X value would be matched up with two Y values, like what is happening over here. All right. If we go to the X value of 4, this one, X value of 4, has two Y values it's matched up with. It fails the vertical line test. This vertical line touches the graph in two spots. So this one is not a function. Okay, y'all have all seen that before, but that's all it is. That's all being a function is. You can't have points directly above and below each other, because that means an X coordinate is sharing two separate Y coordinates, right? Ryan Tannehill cannot throw 15 touchdown passes and 20 touchdown passes in the same year. It's one or the other. Hopefully it's the one with more. All right, so here are two more examples. We have our inputs, our X, and our Ys. So whenever it's listing the ordered pairs, we just need to look at the X's. Are there any X's that are repeated? And yes, the 2 is repeated. So this 2 is matched up with two Y values. This is saying Ryan Tannehill threw 11 touchdown passes. Ryan Tannehill threw 10 touchdown passes. Can't happen in the same year. This is not a function. This one, they're just individual points. -1 has one value. -2, 1, 0, 1, 2. Bar passes the vertical line test. That is a function. All right. So there we go. That's just the answers to those we just talked about. All right. Let's see what this says. In algebra, it's common to represent functions by equations. So we deal with equations more than we do with individual points. Okay. For instance, the equation y equals x squared represents the variable y as a function of x. So this is where we get to solving for y. We always like to solve for y. These puts us in function form. It also allows us to enter graphs and stuff into our calculator when it's solved for y. In this equation, x is the independent variable, y is the dependent variable. The input is the x, the y is the output. The independent variable is the variable you would input. The dependent variable, or is the output. It depends on what you input into X. All right. The domain of the function is a set of all values taken on by the independent variable X, and the range of the function is a set of all values taken on the dependent variable Y. We'll talk more about the domain later. We're not going to really talk much about range today, but the domain is all the values of X that can be used for a relation. And before we go on to function notation, I want to talk about two equations right here about whether or not they are functions or not. Okay, this one, y equals x squared, you can always graph it, right? Let me see if I can get my my calculator up. Let's see. Nope, there it was. I didn't see it there. All right, so if I wanted to graph x squared, right, we can graph it. It's a parabola. This is a function, right? There's no points. The vertical line, it passes the vertical line test. Okay, so that's no problem. Now, the next one, get all this stuff back out. All right, this one right here, before we could graph it, we would have to solve for y. Okay, so I don't want you to know notice what happens here is when we take the square root, if you remember, the opposite of squaring y is taking the square root. When we take the square root of x, if you remember, we have to include both the positive and the negative of that value. All right, the positive and negative of value, like if I put plus or minus 2, that represents two numbers. It represents 2 and it represents negative 2. Well, this represents two numbers. This represents the square root of x and the negative square root of x. Now look what has happened. Y is being compared to two variables or two values. Ryan Tannehill has thrown this amount of touchdowns and this amount of touchdowns in the same year. That can't happen. So this is not a function, therefore it could not be written in function notation, which we're going to look at next. So whenever you see a problem that has the x and it has the y squared, the y is squared, it's not going to be a function. What it ends up being is a parabola that's on its side. And obviously you can see there by the vertical line test, it does not pass. All right, so be aware of that. When you see the y squared, it's not going to be a function. All right, so let's move on to function notation. Once we have a function, and y'all are all very familiar with this right here. For example, we write the equation with x's and y's, y equals 1 minus x squared. This describes y as a function of x is the input, y is the output. Suppose you give this function the name of f, and you can use the following function notation. And here is the function notation. The input is the x, the output is the f of x, the function of x. And then you can rewrite the equation like this right here. F of x equals 1 minus x squared. It means the exact same thing like this right here. Whenever you see f of x or g of x or h of x, they use different letters because it gets confusing if you just use f of x all the time. You have more than one equation. Same thing. X is the input. What do you put in for x is going to equal to whatever f of x is. Okay, so that's function notation. You've all seen that by the time you get here into pre-cal. All right. And what we want to be able to do is say we have this function value right here, or that function. What is the function value when the input is -1 and the input is 0? Right? So what we do is if we have f of -1, okay, notice -1 is my input, so my x is my input over here. So all I do is I'm going to put -1 in for x, and then I'm going to end up with 3 plus 2 equals 5. So the function value at -1 is equal to 5. F of 0 is going to be 3 minus 2 times 0 equals 3 minus 0 equals 3. So f of 0 equals 3. So the function value at 0 is 3. We could also write that as an ordered pair. Since the x is the input, the x was 0, the output or the y was 3. Same thing here. This would be the ordered pair, negative 1, 5. All right. Here are all different. Notice here f. You can use f of x. Then the x is going to be over here. If we're looking at a function of time, a lot of times they use f of t, where now we have t's over here. Here they're using g of s. Maybe they're looking at some sort of function of seconds, s squared. So don't get locked into it has to be f of x. It could be f of t, g of s. It's all the same thing. Okay. These are all, notice these are all the exact same function. They've just changed the variables. Okay, nothing to get alarmed about there. All right. Right, it's a placeholder. I'm not going to go over that. We've got that. All right. Now, I do want you to look at this quickly. G of 2, and here is our function value up here. And I'm just going to write it out. Now, you do have to be careful whenever we start having negatives. All right. When we have a negative exponent right there, all right, whether what you're putting in or whether you have a negative out front, it is very important that you put the input in its own little sets of parentheses. All right. Because what's going to happen, if you're doing a mental math, you might be all right. But if you're using a calculator treats this, all right, here different than that. All right, here it's not going to square the negative. Here it will square the negative. Okay, so be very careful there. And then we know 2 squared is 4, so this is negative 4 plus 8 plus 1, which is going to be what, 5? All right, if it's g of t, we just plug t in for wherever there's an x. And that's it. That's all we can do. There's nothing else we can do to simplify that. All right, g of x plus 2 gets a little bit more complicated, but it's the same deal. All right, wherever there's an x, we're going to put in x plus 2. The input is x plus 2. X plus 2 squared plus 4 times x plus 2 plus 1. Now you would have to multiply this out, so that's going to be negative x squared plus 4x plus 4. Distribute the 4 plus 4x plus 8 plus 1. And then when I simplify all that out, right, we've got, I forgot to close my parentheses. This negative has to distribute there. So that's going to be negative x squared. That's going to be negative 4x plus 4x, which is 0. That's going to be negative 4 plus 8, which is 4 plus 1, which is positive 5. And that's how that simplifies. All right. But same deal. All right. 5, just showing the answers there. That's negative x squared plus 5. All right. So that is all we're looking at to do right now with the function notation. Now let's talk about domain of a function. We said earlier the domain is associated with the input or the x value. All right, if you were looking at a graph, the domain would be all the x values that this graph touches. All right, so let's say it's a line. If it were a line, all right, well, the x values are, so how far does this go to the left and how far does this go to the right? Well, it goes forever to the left, it goes forever to the right. So this would be a situation where the domain would be all real numbers. Okay, and let's move on. Let's see what their definition is. I'm sort of getting ahead of myself there. The domain of a function can be described explicitly or it can be implied by the expression used to define the function. The implied domain is a set of all real numbers for which the expression is defined. For instance, this function right here, f of x equals 1 over x squared minus 4. All right. The domain is all x value, basically represents all inputs we could come up here and have a defined function. Well, what we know is if 0 is in the denominator, it is an undefined function. So what values of x, or what inputs would cause this denominator to be 0? Well, if x squared was equal to 4, 4 minus 4 is 0. Well, what two numbers when squared equals 4? Right down here, plus or minus 2. So the domain, or all the values of x that can work here, are all real numbers other than 2 and negative 2. Okay, because we cannot divide by 0. So that's the domain of this function. It would be all numbers except x equals plus or minus 2. So that's how we would write it. We're going to talk about interval notation here in just a minute. Another place where we run into this is square root. If we have a square root, let's say we have f of x equals x plus 2, right? We're dealing with real numbers. We cannot take the square root of a negative number. So the domain for this one would exclude any number that's going to cause this inside of here to be negative, right? So basically any number bigger than 2, any number smaller than negative 2 would cause this square root to be negative, right? If I put in a negative 4 plus 2 is negative 2, undefined number. All right, so what I would have to say here is my domain is going to be what? X has to be greater than or equal to, nope, yep, it can be negative 2, because negative 2 plus 2 is 0. The square root of 0 is 0. So my domain here would be all x's that are greater than or equal to negative 2. All x's greater than negative 2 would make this okay. Anything less than negative 2 would cause a problem, okay? And here's that example again. And while we're here, I want to talk about interval notation. It's another way to write inequalities. Okay, so same thing here. F of x equals the square root of x. We know that x has to be positive. So x has to be greater than or equal to 0. All right, now another way you can write x is greater than or equal to 0 is using interval notation. Interval notation, basically, it uses either brackets or parentheses, and it always has a comma in the middle. So you could have bracket to a comma to a bracket, bracket to bracket, comma to comma, to parentheses, bracket to a parentheses, parentheses to a bracket. The comma separates where it starts. Okay, so notice how they wrote the interval 0, infinity. All right, x is greater than or equal to 0. Well, the bracket means that it can equal this number. This number is actually part of the solution or the set. X is greater than or equal to. So that's the same thing as or equal to, comma, and then it goes to everything above 0, which means it runs to positive infinity. We always put a parentheses by infinity because infinity is not a real number. Not a number that ever ends. It just keeps going. So it really can't include a number because there's always more. So we always use a parentheses there. All right. If I wanted to say all numbers x is less than or equal to 0, then what I would do is I would go from negative infinity up to 0 and including 0. That was weird. All right. This represents all numbers less than 0. It goes from negative infinity all the way up to 0, or 0 all the way to negative infinity. If I had this, 3 is less than x is less than and greater than 10, this would be 3, comma, 10. All right, or equal to 10 includes 10. 3 less than, parentheses, means 3 is not part of this solution, but this is interval notation. This means it includes all numbers in between 3 and 10, all fractions, decimals, whatever. Okay? So don't know if you've seen interval notation, but we'll be using it some, and that's just sort of a quick introduction to it. All right, so the domains of each function here. Let's just review this real quickly. Here, remember the domains are the x's. So here we just list the x value. So my domain here would be, I'm going to use the little brackets there, -3, -1, 0, 2, and 4. If any of them repeated, I would not need to write them down twice. All right. This one right here is just ends up being a parabola that opens downward. We could actually go back and we can look at our calculator. So what is that? -3x squared plus 4x plus 5. Let's see, -3x squared plus 4x plus 5. That's close enough if that's not it. All right, if that's just a parabola opening down. All right, this continues to go forever and ever down and out, down and out. So this is an example that the domain is all real numbers. This will keep going. This will keep going. There's no breaks in it. There's no problems with that. So that is all real numbers. All right, if you want to write that in interval notation, you could write either all reals. If you wanted interval notation, it would just be -infinity to infinity. That's all numbers. All right, C is going to be all numbers, except what's the one number that would give us a problem? What's the one number that would give us a 0 in the denominator? And that would be -5. So we could say all reals x cannot equal -5. If I were doing interval notation, what I would do is I would say it goes from -infinity up to -5, and then -5 to infinity. Notice I didn't include 5 in there, so this is representing all numbers except for -5. All right, what about the absolute value? All right, the absolute value of x plus 1. There's no number. Basically, you don't even need to look at the graph. Absolute value has a V graph, but if you'll notice, there's no number I can put in for x that's going to cause me a problem, right? Never. So this is going to be all reals. All right. Now, what about this one? The square root of x minus 4. Remember, we cannot have a negative inside the square root. So one way we could look at that is x minus 4 has to be greater than or equal to 0. So one way we could solve for the domain there is we could add 4, and we could have x has to be greater than or equal to 4. Right? We could write that as comma. Nope, not comma. I keep saying comma for parentheses. A bracket, 4 comma infinity. Okay, so there we go. I don't need to go through all these because that's what we just talked about. All right, a couple of application problems. We're getting close to the end here. All right, let me get rid of all this jazz up here. All right, the number N in millions of employees in the construction industry in the United States increased in a linear pattern from 2003 through 2006. All right. So here, notice year 3 is 2003. So they said a linear pattern from these 3 years right here. We're just making a line. All right. But if you notice, it's bounced around. It did no longer make a line anymore. After that, all right, in 2007, the number dropped, then decreased through 2008 in a different linear pattern. These two patterns can be approximated by the function this right here. This is what is called a piecewise function, right? Where there are pieces of the function. All right, when the value of t is in between 3 and 6, this linear equation holds true. Once it gets to 2007 and 2008, this linear equation takes place. So if you're looking at values of t, if it's between 3 and 6, you would use this formula. If it was between 7 and 8, you would use this formula. Okay, if you notice, go back to the graph. That's the line of the first 3. Here's the line of the last 2 between 2007 and 2008. Now let's see what they ask us here. All right, t represents the year. T equals 3. We're responding to 2003. Use this function to approximate the number of employees for each year from 2003 to 2008. So basically, this is wanting to know n of 3. It wants to know what is n of 4, n of 5, n of 6, n of 7, and n of 8, right? It wants to know what it is, what's the input for each year. The year is the input. They want to know what's the output for each one of those years. So for 3, 4, 5, and 6, I've got to use the top formula to find my output. For years 7 and 8, I've got to use my bottom formula. And I'm sure they do this for us here where I don't have to. So basically, we're plugging in 6.66 for T for 2003, 6.98 in 2004, so on and so forth. Then once we get to 7 and 8, we're not inputting 6.6, I'm sorry. When we plugged in 3, we got 6.66. When we plugged in 4, we got 6.98. When I got plugged in 5, I got 7.3. When we got plugged in 6, we got 7.62. Then when we got to 7, we had to use the other formula, plug in, we got 7.56 and 7.14. Okay, that's a little introduction to a piecewise function. You got to pay attention to what the input is so you know which equation you need to use. And that looks like the end of it. We will open up assignment 1.2. All right. For you distance learners, join us in class if you need to ask questions or whatever. But that's it.